I'm Alice. I'm also here representing ZKM. ZKM is a zkVM, similar to Nathan, who was presenting about succinct. We're both ABMs. We just have different design considerations. For this presentation, I'll just be going into more on the first part, the intuition behind using ZK, why we're building its UVF. Then from there, go into some more architectural design considerations we made, and then do a quick demo of how you can use our project template to build your own ZK applications. And we'll also be discussing about some use cases, including the Go network, which is being built on ZKM right now. First, what is ZKM? ZKM is building a general-purpose zkVM called Ziren for verifiable computation that's based on MIPS. This may seem like a bit of a mouthful, so we'll be going into what each of these terms mean one by one. First, with verifiable computation, in this part, I just want to quickly talk about kind of the status quo with how we've been dealing with verifying our population. So when we ask the question, how do I ensure that my computation was correctly done? There are two ways of doing this. One, you can outsource that computation to, say, to some external third-party cloud service providers, say to AWS. Good thing about that is that you don't have to do any of the running the computation on your own end if, say, you don't have the hardware requirements to do so. But the problem with that is that there's this trust component involved. You have to trust that that third party like AWS is performing that computation correctly. The other model that you could use is self-verification, so that this is just running this on your own. And that's better. It's, say, you're building some sort of privacy-based application, or if you have some private inputs, you just want that locally. It's more secure that way. But the issue is that with that is maybe don't have the computational or hardware requirements to do so. It could be, in terms of costs, pretty computationally expensive. So each of these models for like the current ways that we're using for verifying that a computation was correctly done, they each have their cost balances. Now for a proof of knowledge, what this is, it's a two-party protocol which allows a prover. Typically, this prover will have some more computational resources. It could be like, say, some servers in the cloud to convince that some verifier, this verifier, for example, is a user like us, that it knows a valid solution to a computational problem. So how this dynamic kind of works, what we mean when we talk about proofs. So we have this prover, we have this verifier. If the verifier will ask the prover, please compute, like, for example, say y equals some kind of function for me, that prover will compute that. And in addition to that execution result, will produce an accompanying proof that proves that that execution was done correctly. Now, both that proof and that result will be sent back to the verifier. So that's kind of the dynamic that is involved with the proof of knowledge. In terms of just some examples of computational problems, technically for ZK, any kind of N-key related problem can be modeled as an arithmetic circuit, and then you can use ZK to prove that. So the number of computational problems that you can use for these proof of knowledge is quite intensive, quite extensive. But just some examples, like, for example, proving the prime factorization of a given number. That's a very common toy example that a lot of zkVMs use in their examples, proving that the correct private key corresponds to the associated public key for authentication, or even proving, for example, the validity of an ECDSA signature used in signature verification. Those are just some examples of what we need by computational problems. So you may be wondering, like, why do we need to do all this work where the prover and verifier has all these interactions between them? Why can't you just simply rerun the program or just reveal the solution? Now, there are two problems to this. One, on the verifier side, if you rerun the program, your resulted proof might be too long. One of the properties that we need to consider for proofs is succinctness, which was mentioned before in the previous talks. So we want our proof to be short and as easy to verify as possible. So making sure that our verifiers work So in this case, the user's word is as simple as possible. On the other hand, in terms of revealing the solution, that maybe the prover wants to keep the solution a secret. This is where the zero-knowledge, the ZK component comes in. Sometimes in the case where you have some private inputs, perhaps you want your proof to not reveal any kind of information about the solution. So within the proofs of knowledge, there are two types of proofs. There's our succinct proofs and then there are ZK proofs. ZKM or ZKVM, we're focused on building succinct proofs. You do have the option of making those proofs zero knowledge, adding that privacy component, but our main focus here is generating those proofs. So that's just kind of like nuance in terms of terminology. In the industry, oftentimes people say that they're using ZK proofs. What they really mean, they're using succinct proofs. So just wanted to point out that difference in the terminology there. When we're applying these proofs of knowledge to blockchains, some of the properties that we need to consider, non-interactiveness between the proof and verifier. That makes it so that multiple parties can verify a proof. We want our proof to be succinct or short. The ZK ASCII over here is optional. Some examples of some computational problems that we see within blockchains. For example, you guys can all be familiar with ZK rollups and think of those as transition functions for L2s. It's a very popular application for verifiable computation. Basically here in our prover verifier setup, the L1 acts as a verifier. To think of it as a computer in the cloud. Perhaps there are some issues with scalability, which is why they want to outsource kind of those computations to the prover, which is the layer 2 here. So those computations are outsourced off-chain from the layer 1 onto the layer 2. And the L2 will send that result to root state with an accompanying proof back to the layer 1. So that's how the prover verifier dynamic happens within ZK rollups. But another computational problem are ZK EVMs. ZK EVMs, you can think of as like a special case of a zkVM to prove the execution of smart contracts. ZKVMs, you can think of kind of like the umbrella that includes ZK EVMs, but that's extending it to more general purpose applications where you can prove the execution of any type of off-chain program. Now we're applying these proofs of knowledge to Ziren, which is ZKM's zkVM. Basically for Ziren, our objective here is to verify on-chain that a program that was compiled to MIPS. MIPS is the instruction set architecture ISA that ZKM is using was correctly executed off-chain. So our computational problem here is to verify the correct execution of a program, and our solution or that proof of correctness comes in the form of an execution trace. And that execution trace you can think of as a complete record of that computation. And in its form consists of like a sequence of the states that represent each instruction of that execution. And for the verification process, it just involves checking that each row of that trace matches the respective instruction of the program. So after that program is compiled down, for our case to MIPS, you'll have a sequence of instructions. So you want to make sure that each row matches there. And with some examples of programs to verify, for example, practice of some transactions, it could be used in rollups as well, and we'll go into more details about that use case with Goat Network, which is a Bitcoin layer 2 that uses Ziren. Even, for example, a lot of zkVMs are involved in an initiative called ETH Proofs. This was funded by the Ethereum Foundation. Essentially, they want zkVMs to be able to provide proofs of the execution of Ethereum mainnet blocks. So instead of having the validators re-execute those blocks, they would just need to verify a proof, and it's a lot cheaper to do that. It's a lot faster. So now there's this initiative, there's kind of like this race for zkVMs to get towards real-time proving. So being able to prove these mainnet blocks in real time. Those are just some examples of programs that you can verify using zkVMs.
Hey, Alice, ask a question?
Yeah.
Land it.
Hi, Leo.
Hi.
Yes.
I had a maybe a silly question, but we say like the L1s are the provers, and the L2s are the verifiers, and anything like that. Is that in relation to like your Ziren being an L1 and like all of them being an L2, or is it different L1 and L2 framework like that actually sort of like the ZK phonetics?
You can so for any kind of L2 that is using ZK proof, you can think of that as like a ZK rollup. So for example, for our case with Goat Network. Goat Network is a Bitcoin based layer 2. And that is the ZK rollup that's Bitcoin based, and the that's the L2 portion. The L1 is Bitcoin itself.
So how would that look out like Ethereum? I think ZK is a little more famously used on Ethereum, right?
Yes, you can now like for right now, Ethereum, yeah, it's the main kind of use case. Now there's some through paradigms such as BitVM, there's some capabilities where you can use Bitcoin as well. But it's essentially like very similar. You can apply that same model to Ethereum or to any kind of chain. For Ethereum, any kind of like EVM compatible L2 that uses ZK can be considered as a ZK rollup, and you can apply that same.
And is that you're saying that they use ZK on Ethereum and it's scalable, use it on Polygon or other chains, then it scales better and it's cheaper. Is that kind of how?
Yeah, for L2s, that's the case. That's the main value prop. So these L2s, yeah.
But you can run ZK on Ethereum if you want it.
Yeah, I get. Thank you. Yeah, thank you, Landon. Now for our next section with ZKBX, going into some more details about that. Before we dive into what zkVMs are about, let's just quickly go over kind of the general setup for a VM. A VM you can think of as a program that can run other programs. So an EVM, think of as a VM that runs smart contracts in Ethereum. Essentially over here, you have some sort of input, like a public output. You have a program, both that input and that program that's fed into the VM, and what's outputted is this kind of final state. So that is the general setup for a VM. zkVM has basically the same setup, but with a few extra components. So in addition to your inputs in a program, you have a witness. That witness could consist of some secret inputs that you'd like the verifier to not know about. All of that is fed into the zkVM. And then in addition to your output, you have an accompanying proof that proves the correct execution of that program that you inputted with its accompanying inputs. Now, why do people use zkVMs? We'll quickly go over kind of the proof lifecycle, what happens when proofs are generated. So first, there's some ends of action. We need to determine what exactly will be proven. And then the case of zkVMs, they're able to execute these programs, but the main question there is how will this be executed? From there is the proof generation part. So we need to address how can that proof be generated. From there, how can that proof be verified? For on-chain verification, so all the time you can just verify that via smart contract, or there are some verification layers that exist as well that can be integrated with zkVMs or just with the like proving networks. And then from there, there's some kind of resulting action where you can determine how will that proof be used. But here is the question: what if this proof of execution can be provided for any type of general commutation, not just those, say, within, like, say, Web3 or just like blockchain-based transactions? For zkVMs, the main value proposition, like what ZKM has, also other zkVMs that exist in the market, one is that it suffers any type of general computation, and another is that it really simplifies the developer experience. So I remember Nathan in his talk, namely from 6.8, he mentioned that the traditional way of using ZK is hand-rolling circuits, writing these circuits. But now with ZK, developers don't need to do that anymore. They can just use programming languages that they're already familiar with. For example, many ZK VS or Paparuras, Ziren itself, this will help. Though as well, bleach, palette solidity. So instead of having to learn a new language, you can just use languages that you're already familiar with, write a program and generate a proof for it. So over here, the ZKBM really kind of secures let me, oh my, there we go. Hopefully you guys can see it right side now. It supports all of these steps within the life cycle. So for the, oh, thank you. Apologies if you guys couldn't hear me too well. I just can't. Oh, got it. Okay. Hopefully you guys can hear me a little better now. So ZKBMs here are able to address each step of this life cycle, including how it will be executed. Each ZKBM consists of prover to assist with the proof generation, proof verification. For us, you can just use a contract to verify it on chain. And in terms of how it can be used for both blockchain and non-blockchain use cases. So the extensibility there is pretty wide. And in addition, why use a ZKBM? We talked a little bit about circuits. So you can see that the setup here in terms of what goes into the circuit, what comes out is pretty similar. But the programs you need to write in, say, either Sergom. There are some ZK domain specific languages that are maybe like a level above handwriting those circuits. So for example, Leo, that's developed by Aleo. Noir, that's developed by the Aztec team. Noir, for example, uses Rust-inspired syntax. So developers who are already familiar with Rust can learn Noir fairly easily, but you still need to learn another language. So there's still that barrier there. ZKVMs are one abstraction layer on top of EQDSLs. So you can think of this as like before people were writing in assembly, but now, we have a lot of other higher level programming languages that are just a lot simpler to use. So you can think of that as kind of like analogous to how we've come from circuits to these domain specific languages to now these ZKBMs. And just as some comparisons between these two approaches. When you're using a circuit, the program is equivalent to the circuit, and the circuit is specific to each program. You need to define a special verifier each time. For the ZKVM, though, you can think of the program as an input to the ZKVM. ZKVM is reusable for any kind of program that you want to input it. And in that way, it makes it very similar to kind of like a universal circuit. You only need to define the verifier once. And then, as we mentioned before, for circuits, devs have to use kind of like specialized methods. ZKVMs, devs can use languages that they're already familiar with, higher level languages. Circuits, you also have to have additional knowledge, for example, with defining constraints. You need to have some knowledge relating to cryptography. There's just like a lot more, the steeper learning curve in terms of being able to write these circuits as opposed to using ZKVMs. But there are still trade-offs with using ZKVMs. Circuits still have their advantages. Circuits are pretty optimized. They're efficient. With ZKVMs, you may have to deal with some overhead, like related to memory, for example. So that's why people still use circuits. And like for the case of precompiles, for example, I know that the 6-Inc presentation went over this a bit. There are some like specifically cryptographic operations that can be accelerated if you define specific circuits for them. So some of the ZKVM teams do still write circuits for specific operations just to help accelerate certain aspects when it comes to proving a program. So there's still a value proposition there. It's just that nowadays, in terms of just regular developer adoption, ZKVMs are preferred, and they have that kind of plug-and-play model. Now, for next, MIPS is the ISA that ZKM is using. All our programs are compiled to MIPS. Some of the reasonings, like why the team chose to use MIPS, has a pretty established system, has been around for around 4 decades already, has pretty good compatibility as well. It's pretty stable, comprehensive in terms of like compatibility. For example, a lot of IoT devices are based on the MIPS architecture. So the ZKM team in the future is thinking about extending its applications to proving IoT devices. Even often in sense like fault-proof VM is MIPS based, so has pretty good compatibility with many different systems. It just some other like intricacies relating to why the team chose MIPS. There are some instructions that are pretty efficient. There is another type of ISA called RISC-V that allows ZK BTCFi use. MIPS is a superset of RISC-V. But compared to RISC-V, MIPS has some special instructions like this multiply add, multiply subtract, and it can reduce the execution trace of your program, and it can lead to greater proving efficiency. And it's difficult to support these instructions for RISC-V. So there are some like little subtleties as to why the team chose MIPS instead of RISC-V. But either way, it is a superset of RISC-V regardless. But those were just some of the main kind of decision points that the team took into choosing this specific might say. Now, going into some more details about Ziren itself, which is our zkVM. Here's the overall step-by-step with what goes on from your program to generating your proof and then to verifying it. It's split into these three main components. First, executing your program, generating your proof, verifying it. I'm going to go over this section quickly just because it's just like a very high-level overview of what happens under the hood. We have some more information about these details or evokes, but just to go over very quickly, you start out with your program. That program is written in some kind of higher-level language. For example, right now we have compatibility with Rust and Go. That program is using our piler is piled to a MIPS ELF. That's the executable format. And basically, the ELF will be loaded into the MIPS VM using a loader. That VM will run that held program, and that result of the execution is an execution trace. Remember, the complete record of the program that's generated for the prover to use. Now, just some more details of what that looks like. After your program is compiled to MIPS, you'll get a sequence of MIPS instructions, which is on the, for example, on the left side. After each instruction is executed, you'll get a value for a register. So, for example, row I, the left side, it's basically saying add the value from register 5 to the value in register 6, store that in register 7. You can see on the right side, that is our trace table. So to see kind of the interaction happening there with row I, row 70, the value stored there is 34 because the three one is 34. But basically, this is kind of like a simplification of what happens during the proving process. But the main point here is that you execute each instruction, each individual instruction, and then store that as a record in a resulting trace table. Now, the prover will use that execution trace that is generated. So what's on the right side here. And as part of the proving process, we go through quite a few different steps. The whole point of this, like, for example, dividing our program first into segments and dividing that further into different modules. The whole point of this is to make our last truth as succinct as possible. So over here, we first split our trace into segments. Those segments are divided further into modules, and they're divided into their respective tables. Like, for example, any kind of arithmetic-based operation would be added into an arithmetic table. Any logic-based operation would be added into the logic table, so on. And then from here, those modules are proven independently, and eventually will be able to have a proof that is generated for each type of table. Now, linking them all together, we use a lookup protocol, and that's able to basically combine our proofs together recursively and into one single continuation proof, and that will prove the correctness of the entire program trace. And then to make it compatible with on-chain verification, we wrap that start-based proof into a snark-based proof. So, for example, with Groth16, and then from here, after you receive your proof, you can now do some on-chain verification with it. So that's just a very high-level overview of what happens under the hood. But as you could see for the overview, remember these steps from the proof lifecycle. Here are kind of what the interactions that happen with Ziren corresponding to those steps within the proof lifecycle. So we have our program that runs in Ziren's execution environment, compiles it to a MIPS-based program. A proof is generated, and then we can verify that proof in the case of any kinds of blockchain-based transactions. Once that proof is verified on-chain, it's considered to be settled. And here are just some other kinds of design considerations that the team consider. In terms of use cases, ZKM is building from the team is building the first layer 2 on ZKM's Entangled Rollup network. So May, actually, from our team, he's here today. He gave a talk over the weekend about Entangled Rollup. But essentially, the vision there is that we could have a system of layer 2s that are able to function as interoperability mechanisms and facilitate cross-chain messaging via ZK proofs instead of having to do those cross-chain asset transfers via a bridge, which comes with its own kind of security and trust assumptions. So in this case, we are just inheriting security from the underlying layer 1. In Goat's network's case, that is Bitcoin, instead of some kind of third-party bridge. Goat is by itself, they win ZK Rollup. They did inbuilt sustainable Bitcoin yield generation mechanism. We actually have quite a few members of the Goat team here today. So if you guys are interested in learning how you can generate yield for your Bitcoin Goat, and check in with our team. But essentially how Go uses ZKM to generate proofs of their blocks on demand, and proof verification is done on Bitcoin itself by implementing verifier strips on top of a BitVM verifier. BitVM is a paradigm that makes Bitcoin more programmable and enables for optimistic verification of arbitrary computations right now in Bitcoin. So, for example, in our case, it would be a Groth60 proof. And in terms of building on Goat, it's 100% EVM compatible, and we have a few different developer tooling that's available for our devs. We have a subgraph service. We have some oracles if you want some real-time verifiable data to be used when you're building your dApp. We have some DRF contracts to integrate some randomness, especially if you want to develop some GameFi-based apps. That could be very helpful. And here's just a link of kind of all the pre-deployed protocol contracts. But if you want to learn more about how you can create your own dApps on Go, we have a quick start guide available. You can just go over to docs.goat.network. Now, in terms of the Ashmo demo, I am wondering if we can, so it looks like we can use my laptop for this. A sample host and guest program for proving the Fibonacci sequence, some inputs correspond to the correct numbers in the Fibonacci sequence utilizing our project template. So from here, we can compile our program to our MIPS executable, generate a proof, and then deploy a verifier contract, and then post that proof on that contract. So in terms of program execution, some of the things that you need to consider when you're writing programs, there are two different types of programs. There are finity written within our ZKVM. So one is our guest program, and then the others are host program. The guest program will execute the ELF that's pre-assigned to zkVM and also includes any type of program logic that you want to be encoded. And we'll go over into what the guest program looks like for the Fibonacci example. We need the project template. The host program will set up the environment for that guest program and evaluate the results from this execution. So the guest program will read the inputs that's provided by the host. It'll write those private outputs to the host, commit it. The host will evaluate those hybrid outputs. And those are just kind of the main interactions that happen between the guest and the host. So, for example, this is our guest program for the template that's for the example, the Fibonacci example within our template. In our made function, you can see that first we're reading it in with the host. You're encoding the logic for computing the Fibonacci numbers. And then we are committing it to the public output so that the verifier can validate that that output matches the following input. And then here is the logic for the host. So in kind of like our main argument here, we're setting up the inputs to be read from the guest. We're executing the program and then reading the output. And then you want to set up your proving key and verifying key as well to generate it. And then there are different options that you can use for the type of proof that you want to be generated. So we have a core proof, a plus proof. We also have some ZKVM compatible proofs like the cloned ROT16 proof. It is recommended that you use the ROT16 proof for verification, even though it is the trusted setup. It's smaller in size compared to the hot proof. So that's some of the logic that is within the host program itself. And for proof generation, just go over very quickly. There's two types of proof generation. You can either do this locally on your machine. You would also outsource your proof. So a lot of ZKVMs, including us, have a proof network available. You can outsource your proof generation to our proof network. And an alternative to local-based proving, especially if you don't have the hardware requirements or you just want faster proof generation, especially for more computationally expensive workloads. The remote proving via our proof network may be the better option. So you can go ahead and apply for a spot on the whitelist. I'll show you guys the link for that later on. I believe I have a slide for that. So you can just go on to zkm.io/apply if you want a spot on the whitelist. Now for the verification part, you have the capability to verify our proofs on chain and via deploying a contract. And then when we're generating our proof, what's also generating is our verifier key, and that's used to generate your verifier contract. It's specific. It's specific to the proof that was being generated, and that deployed verifier contract with that post proof will determine if that proof is valid or invalid. So now we can finally get through our walkthrough. So when you guys are doing this on your own end, we have an installation guide. Be sure that you have these requirements for Rust-Ego. You can go ahead to our project template. The link is right over there if you want to try this out on your own later on. But be sure first to go to the installation within our docs. It'll specify the toolchain that you need to install. And then what you can do is just clone this project template and make some changes on your own. So let me go ahead and share the project template that I cloned. Okay, I'm in the exit out here first, and that. Over here on the first Linux, you'll have a few different directories. The host will contain your host program. We can see, so here, this is the host program we saw in our previous slides. And the guest directory will consist of the guest program that we just saw. Some of the contracts that are included, we have a few different test contracts for deploying specifically the Higurashi program, but you can create your own test contracts as well. And just tailor the main host program and main guest program for any kind of use case that you want to build off of. So I have over here some of the commands that you'll be using to, which are also listed in our quick start guide. But over here, if we first say that we have our, the project template, by the way, is ready to go with that Fibonacci example. So if you just want to test out to see if everything is working correctly, you can generate your proof, you can verify it. Just run through these commands first. Let me just over here. So if you're testing your program and you want to reveal the public outputs, but without generating the proof itself, just for testing purposes, it is recommended that you just use the execute command. So you can just display your outputs without having to gate before you go ahead and update testing phase. So we'll go into our post program, and then use that command that's right above the cardo run release, and then execute. So over here, this will just be generating the outputs, so evaluating if the Fibonacci numbers that we computed were correct. And then you can also display the number of cycles, and that's pretty helpful if you want to figure out which parts of your program you want to optimize for. You can know how many cycles were being generated for each type of MIPS cycle. That's a helpful benchmark. So that's for just the executing. And if you are ready to now generate your proof, the quick start lists all the different types of proofs that you can use to generate. If you want to generate your ROS16 proof, we'll do the command for that is just cardo run release, and then yep, and then specify that you are using ROS16. Did I spell this incorrectly? Oh, it looks like I need to have another done the dash. So let me just, and of course when you're doing this on your end, easier to just copy paste the commands. So cscans ROS16. And depending on the hardware that you're using for this, it may take some time. On my end, I give it to around 5 to 6 minutes to generate the ROS16 proof. So we won't wait it that long because I know I'm over time already. But essentially, after your proof is generated, it'll be stored within your contracts directory. And there should be fixtures and the contents of that proof generation are stored in this ROS16 fixture. And just to know, if you don't want to do local proving, you want to use the network proving via ZKM's prover network, just specify over here, but you want to use network instead, and then follow the steps for the Dutch integration. So that's just a note over there. I did generate a proof prior to this. So what that proof was look like is over here. This was a ROS16 proof that I generated for this exact program, and it's outputted. We have a verification key, the public values, and those proof bytes that will all be used for our next verification step. So I'm sporting to pause the proof generation. It will take some time. Great. And then once you have your proof generated, we have some test files that you can use to verify that everything is working correctly. So just going back over here, go into your contracts directory, and we're using Foundry for this, so we can just use our Forge test. Over here, all of our tests have passed, and once you're ready to do that, you can deploy your contracts to some sort of EVM compatible network. For example, with Sepolia, just specify the endpoint that you're using, and then also the key that's corresponding to your wallet, and you can broadcast that over and verify. We'll create the contract, and then you can see the verification from there. So those are just like some of the main steps that are all outlined on the quick start that you can follow through with how you can first execute your program, generate a proof, verify it, and of course, for his audit template, you can do modifications regarding with the main host and guest program that you want to use, as well as the test files. So there's a lot of flexibility to use the product template here. But that should be it. I know that I have run a bit over time. So thank you all for sticking out with me, and just some more resources over here. But yeah, thank you so much. Everyone, day. Hey, Landon, I'm not sure I have time for questions. If I don't have time for questions, I'll be sitting around for the entire event. So, we'd be happy.
Usually chat. There's a pressy question, two pressy questions. All right, yeah. Go ahead, run back there. The mic. So I'm just wondering, you said there's you were here put the private key, so it's not, you're not revealing your private key, right? Because if within the system itself,
yes, we're not revealing it. It's just being used so you can deploy that contract. But for right now, we're still in the test network, so I suggest you just use a wallet that you don't actually use. Put some test you found there and just try it out from over there.
You mentioned that part of the proof process is dividing into segments, and electric segments into module based on like arithmetic, logic. What's the reason for dividing into those modules in that way before Shuri?
Yeah, so that's just a way to make it more succinct. So we first want to create those individual proofs that correspond to those different module tables, and then recursively combine that all into a single proof, and then from there generate a EVM compatible. So doing that is just a way to make it a bit more succinct. The development team that we have at Ziren found that way made the just the overall proof generation process more efficient. So it's the whole point of that is just for improving efficiency.
Thanks. All right, great. Well, thank you, Alice. For Alice, thank you for being here.